University Physics, Volume 1, Chapter 1, Units and Measurements, 1.1 The Scope and Scale of Physics. Learning Objectives. By the end of this section, you will be able to describe the scope of physics, calculate the order of magnitude of a quantity, compare measurable length, mass, and time scales quantitatively, describe the relationships among models, theories, and laws. Physics is devoted to the understanding of all natural phenomena. In physics, we try to understand physical phenomena at all scales, from the world of subatomic particles to the entire universe. Despite the breadth of the subject, the various subfields of physics share a common core. The same basic training in physics will prepare you to work in any area of physics and the related areas of science and engineering. In this section, we investigate the scope of physics, the scales of length, mass, and time over which the laws of physics have been shown to be applicable, and the process by which science in general, and physics in particular, operates. The scope of physics. Take another look at the chapter opening image. The Whirlpool Galaxy contains billions of individual stars as well as huge clouds of gas and dust. Its companion galaxy is also visible to the right. This pair of galaxies lies a staggering billion trillion miles, or 1.4 times 10 to the 21 miles from our own galaxy, which is called the Milky Way. The stars and planets that make up the Whirlpool Galaxy might seem to be the furthest thing from most people's everyday lives, but the whirlpool is a great starting point to think about the forces that hold the universe together. The forces that cause the Whirlpool Galaxy to act as it does are thought to be the same forces we contend with here on Earth, whether we are planning to send a rocket into space or simply planning to raise the walls for a new home. The gravity that causes the stars of the Whirlpool Galaxy to rotate and revolve is thought to be the same as what causes water to flow over hydroelectric dams here on Earth. When you look up at the stars, realize the forces out there are the same as the ones here on Earth. Through a study of physics, you may gain a greater understanding of the interconnectedness of everything we can see and know in this universe. Think now about all the technological devices you use on a regular basis. Computers, smartphones, global positioning systems or GPSs, MP3 players, and satellite radio might come to mind. Then, think about the most exciting modern technologies you have heard about in the news, such as trains that levitate above tracks, invisibility cloaks that bend light around them, and microscopic robots that fight cancer cells in our bodies. All these groundbreaking advances, commonplace or unbelievable, rely on the principles of physics. Aside from playing a significant role in technology, professionals such as engineers, pilots, physicians, physical therapists, electricians, and computer programmers apply physics concepts in their daily work. For example, a pilot must understand how wind forces affect a flight path. A physical therapist must understand how the muscles in the body experience forces as they move and bend. As you will learn in this text, the principles of physics are propelling new, exciting technologies, and these principles are applied in a wide range of careers. The underlying order of nature makes science in general, and physics in particular, interesting and enjoyable to study. For example, what do a bag of chips and a car battery have in common? Both contain energy that can be converted to other forms. The law of conservation of energy, which says that energy can change form but is never lost, ties together such topics as food calories, batteries, heat, light, and watch springs. Understanding this law makes it easier to learn about the various forms energy takes and how they relate to one another. Apparently unrelated topics are connected through broadly applicable physical laws, permitting an understanding beyond just the memorization of lists of facts. Science consists of theories and laws that are the general truths of nature, as well as the body of knowledge they encompass. Scientists are continuously trying to expand this body of knowledge and to perfect the expression of the laws that describe it. Physics, which comes from the Greek physis, meaning nature, is concerned with describing the interactions of energy, matter, space, and time to uncover the fundamental mechanisms that underlie every phenomenon. This concern for describing the basic phenomena in nature essentially defines the scope of physics. Physics aims to understand the world around us at the most basic level. It emphasizes the use of a small number of quantitative laws to do this, which can be useful to other fields pushing the performance boundaries of existing technologies. Consider a smartphone, Figure 1.2. Physics describes how electricity interacts with the various circuits inside the device. This knowledge helps engineers select the appropriate materials and circuit layout when building a smartphone. Knowledge of the physics underlying these devices is required to shrink their size or increase their processing speed. Or, think about a GPS. Physics describes the relationship between the speed of an object, the distance over which it travels, and the time it takes to travel that distance. When you use a GPS in a vehicle, it relies on physics equations to determine the travel time from one location to another. Figure 1.2. The Apple iPhone is a common smartphone with a GPS function. Physics describes the way that electricity flows through the circuits of this device. Engineers use their knowledge of physics to construct an iPhone with features that consumers will enjoy. One specific feature of an iPhone is the GPS function. A GPS uses physics equations to determine the drive time between two locations on a map. Knowledge of physics is useful in everyday situations as well as in non-scientific professions. It can help you understand how microwave ovens work, why metal should not be put into them, and why they might affect pacemakers. Physics allows you to understand the hazards of radiation and to evaluate these hazards rationally and more easily. Physics also explains the reason why a black car radiator helps remove heat in a car engine, and it explains why a white roof helps keep the inside of a house cool. Similarly, the operation of a car's ignition system, as well as the transmission of electrical signals throughout our body's nervous system, are much easier to understand when you think about them in terms of basic physics. Physics is a key element of many important disciplines and contributes directly to others. Chemistry, for example, since it deals with the interactions of atoms and molecules, has close ties to atomic and molecular physics. Most branches of engineering are concerned with designing new technologies, processes, or structures within the constraints set by the laws of physics. In architecture, physics is at the heart of structural stability and is involved in the acoustics, heating, lighting, and cooling of buildings. Parts of geology rely heavily on physics, such as radioactive dating of rocks, earthquake analysis, and heat transfer within Earth. Some disciplines, such as biophysics and geophysics, are hybrids of physics and other disciplines. Physics has many applications in the biological sciences. On the microscopic level, it helps describe the properties of cells and their environments. On the macroscopic level, it explains the heat, work, and power associated with the human body and its various organ systems. Physics is involved in medical diagnostics, such as radiographs, magnetic resonance imaging, and ultrasonic blood flow measurements. Medical therapy sometimes involves physics directly. For example, cancer radiotherapy uses ionizing radiation. Physics also explains sensory phenomena, such as how musical instruments make sound, how the eye detects color, and how lasers transmit information. It is not necessary to study all applications of physics formally. What is most useful is knowing the basic laws of physics and developing skills in the analytical methods for applying them. The study of physics also can improve your problem-solving skills. Furthermore, physics retains the most basic aspects of science, so it is used by all the sciences, and the study of physics makes other sciences easier to understand. The scale of physics. From the discussion so far, it should be clear that to accomplish your goals in any of the various fields within the natural sciences and engineering, a thorough grounding in the laws of physics is necessary. The reason for this is simply that the laws of physics govern everything in the observable universe at all measurable scales of length, mass, and time. Now, that is easy enough to say, but to come to grips with what it really means, we need to get a little bit quantitative. So, before surveying the various scales that physics allows us to explore, let's first look at the concept of order of magnitude, which we use to come to terms with the vast ranges of length, mass, and time that we consider in this text. Figure 1.3. Figure 1.3. Image A. Using a scanning tunneling microscope, scientists can see the individual atoms, diameters around 10 to the minus 10 meters, that compose this sheet of gold. Image B. Tiny phytoplankton swim among crystals of ice in the Antarctic Sea. They range from a few micrometers, where 1 micrometer is 10 to the minus 6 meters, to as much as 2 millimeters, where 1 millimeter is 10 to the minus 3 meters in length. Image C. These two colliding galaxies, known as NGC 4676a on the right and NGC 4676b on the left, are nicknamed the mice because of the tail of gas emanating from each one. They are located 300 million light-years from Earth in the constellation Coma Berenices. Eventually, these two galaxies will merge into one. Order of magnitude. The order of magnitude of a number is the power of 10 that most closely approximates it. Thus, the order of magnitude refers to the scale, or size, of a value. Each power of 10 represents a different order of magnitude. For example, 10 to the 1, 10 to the 2, 10 to the 3, and so forth, are all different orders of magnitude, as a 10 to the 0 which equals 1, 10 to the minus 1, 10 to the minus 2, and 10 to the minus 3. To find the order of magnitude of a number, take the base 10 logarithm of the number and round it to the nearest integer. Then the order of magnitude of the number is simply the resulting power of 10. For example, the order of magnitude of 800 is 10 to the 3 because log base 10 of 800 is approximately 2.903, which rounds to 3. Similarly, the order of magnitude of 450 is 10 to the 3 because log base 10 of 450 is approximately 2.653, which rounds to 3 as well. Thus, we say the numbers 800 and 450 are of the same order of magnitude, 10 to the 3. However, the order of magnitude of 250 is 10 to the 2 because log base 10 of 250 is approximately 2.397, which rounds to 2. An equivalent but quicker way to find the order of magnitude of a number is first to write it in scientific notation, and then check to see whether the first factor is greater than or less than the square root of 10 or 10 to the 0.5, which is approximately 3. The idea is that the square root of 10, or equivalently 10 to the 0.5, is halfway between 1, which equals 10 to the 0, and 10, which equals 10 to the 1, on a log base 10 scale. Thus, if the first factor is less than the square root of 10, then we round it down to 1, and the order of magnitude is simply whatever power of 10 is required to write the number in scientific notation. On the other hand, if the first factor is greater than the square root of 10, then we round it up to 10, and the order of magnitude is 1 power of 10 higher than the power needed to write the number in scientific notation. For example, the number 800 can be written in scientific notation as 8 times 10 to the 2. Because 8 is bigger than the square root of 10, which is approximately 3, we say the order of magnitude of 800 is 10 to the 2 plus 1, which equals 10 to the 3. The number 450 can be written as 4.5 times 10 to the 2, so its order of magnitude is also 10 to the 3 because 4.5 is greater than 3. However, 250 written in scientific notation is 2.5 times 10 to the 2, and 2.5 is less than 3, so its order of magnitude is 10 to the 2. The order of magnitude of a number is designed to be a ballpark estimate for the scale, or size of its value. It is simply a way of rounding numbers consistently to the nearest power of 10. This makes doing rough mental math with very big and very small numbers easier. For example, the diameter of a hydrogen atom is on the order of 10 to the minus 10 meters, whereas the diameter of the Sun is on the order of 10 to the 9 meters. So it would take roughly 10 to the 9 divided by 10 to the minus 10, which is 10 to the 19 hydrogen atoms to stretch across the diameter of the Sun. This is much easier to do in your head than using the more precise values of 1.06 times 10 to the minus 10 meters for a hydrogen atom diameter, and 1.39 times 10 to the 9 meters for the Sun's diameter. to find that it would take 1.31 times 10 to the 19 hydrogen atoms to stretch across the Sun's diameter. In addition to being easier, the rough estimate is also nearly as informative as the precise calculation. Known ranges of length, mass, and time. The vastness of the universe and the breadth over which physics applies are illustrated by the wide range of examples of known lengths, masses, and times, given as orders of magnitude, in Figure 1.4. Examining this table will give you a feeling for the range of possible topics in physics and numerical values. A good way to appreciate the vastness of the ranges of values in Figure 1.4 is to try to answer some simple comparative questions, such as the following. How many hydrogen atoms does it take to stretch across the diameter of the Sun? Answer: 10 to the 9 meters divided by 10 to the minus 10 meters equals 10 to the 19 hydrogen atoms. How many protons are there in a bacterium? Answer: 10 to the minus 15 kilograms divided by 10 to the minus 27 kilograms equals 10 to the 12 protons. How many floating point operations can a supercomputer do in one day? Answer: 10 to the 5 seconds divided by 10 to the minus 17 seconds equals 10 to the 22 floating point operations. In studying Figure 1.4, take some time to come up with similar questions that interest you and then try answering them. Doing this can breathe some life into almost any table of numbers. Figure 1.4. This table shows the orders of magnitude of length, mass, and time. Interactive. Visit https://htwins.net/scale2 to explore interactively the vast range of length scales in our universe. Scroll down and up the scale to view hundreds of organisms and objects, and click on the individual objects to learn more about each one. Building models. How did we come to know the laws governing natural phenomena? What we refer to as the laws of nature are concise descriptions of the universe around us. They are human statements of the underlying laws or rules that all natural processes follow. Such laws are intrinsic to the universe. Humans did not create them and cannot change them. We can only discover and understand them. Their discovery is a very human endeavor, with all the elements of mystery, imagination, struggle, triumph, and disappointment inherent in any creative effort. Figure 1.5. The cornerstone of discovering natural laws is observation. Scientists must describe the universe as it is, not as we imagine it to be. Figure 1.5. Image A. Enrico Fermi, 1901 to 1954, was born in Italy. On accepting the Nobel Prize in Stockholm in 1938 for his work on artificial radioactivity produced by neutrons, he took his family to America rather than return home to the government in power at the time. He became an American citizen and was a leading participant in the Manhattan Project. Image B. Marie Curie, 1867 to 1934, sacrificed monetary assets to help finance her early research and damaged her physical well-being with radiation exposure. She is the only person to win Nobel Prize in both physics and chemistry. One of her daughters also won a Nobel Prize. A model is a representation of something that is often too difficult or impossible to display directly. Although a model is justified by experimental tests, it is only accurate in describing certain aspects of a physical system. An example is the Bohr model of single electron atoms, in which the electron is pictured as orbiting the nucleus, analogous to the way planets orbit the Sun. Figure 1.6. We cannot observe electron orbits directly, but the mental image helps explain some of the observations we can make, such as the emission of light from hot gases, atomic spectra. However, other observations show that the picture in the Bohr model is not really what atoms look like. The model is wrong, but is still useful for some purposes. Physicists use models for a variety of purposes. For example, models can help physicists analyze a scenario and perform a calculation, or models can be used to represent a situation in the form of a computer simulation. Ultimately, however, the results of these calculations and simulations need to be double-checked by other means, namely, observation and experimentation. Figure 1.6. What is a model? The Bohr model of a single electron atom shows the electron orbiting the nucleus in one of several possible circular orbits. Like all models, it captures some, but not all, aspects of the physical system. The word theory means something different to scientists than what is often meant when the word is used in everyday conversation. In particular, to a scientist, a theory is not the same as a guess or an idea or even a hypothesis. The phrase "it's just a theory" seems meaningless and silly to scientists because science is founded on the notion of theories. To a scientist, a theory is a testable explanation for patterns in nature supported by scientific evidence and verified multiple times by various groups of researchers. Some theories include models to help visualize phenomena, whereas others do not. Newton's theory of gravity, for example, does not require a model or mental image, because we can observe the objects directly with our own senses. Although models are meant only to describe certain aspects of a physical system accurately, a theory should describe all aspects of any system that falls within its domain of applicability. In particular, any experimentally testable implication of a theory should be verified. If an experiment ever shows an implication of a theory to be false, then the theory is either thrown out or modified suitably, for example, by limiting its domain of applicability. A law uses concise language to describe a generalized pattern in nature supported by scientific evidence and repeated experiments. Often, a law can be expressed in the form of a single mathematical equation. Laws and theories are similar in that they are both scientific statements that result from a tested hypothesis and are supported by scientific evidence. However, the designation law is usually reserved for a concise and very general statement that describes phenomena in nature, such as the law that energy is conserved during any process, or Newton's second law of motion, which relates force F, mass m, and acceleration a, by the simple equation F equals ma. A theory, in contrast, is a less concise statement of observed behavior. For example, the theory of evolution and the theory of relativity cannot be expressed concisely enough to be considered laws. The biggest difference between a law and a theory is that a theory is much more complex and dynamic. A law describes a single action, whereas a theory explains an entire group of related phenomena. Less broadly applicable statements are usually called principles, such as Pascal's principle, which is applicable only in fluids, but the distinction between laws and principles often is not made carefully. The models, theories, and laws we devise sometimes imply the existence of objects or phenomena that are as yet unobserved. These predictions are remarkable triumphs and tributes to the power of science. It is the underlying order in the universe that enables scientists to make such spectacular predictions. However, if experimentation does not verify our predictions, then the theory or law is wrong, no matter how elegant or convenient it is. Laws can never be known with absolute certainty because it is impossible to perform every imaginable experiment to confirm a law for every possible scenario. Physicists operate under the assumption that all scientific laws and theories are valid until a counterexample is observed. If a good quality, verifiable experiment contradicts a well-established law or theory, then the law or theory must be modified or overthrown completely. The study of science in general, and physics in particular, is an adventure much like the exploration of an uncharted ocean. Discoveries are made, models, theories, and laws are formulated, and the beauty of the physical universe is made more sublime for the insights gained. This concludes 1.1 The Scope and Scale of Physics, of Chapter 1 Units and Measurements, from University Physics, Volume 1. Hit the like button and remember to subscribe. Special thanks to the OpenStax team for creating this free online resource.